Thanks again to Roberto, Manuela, and Giuseppe. It's been a challenging week, very exciting. We had an important release of stress. I would say that we are around here. So there will be coffee soon, then Thomas, then discussion, and then we're going for a sunny walk. But I'm sure that something will remain. So let me start thanking the people involved in what I'm going to tell you about, mostly Afshin, who is a graduate student, Marco Caggioni of PNG, and some people in Politecnico, Pavia, and Padova universities. So we are all fond of complex fluids. We are surrounded by them. We are composed by them. Some of them happen to be yield stress fluids. So there is a threshold somehow governing the crossover between the two behaviors. And this is definitely very important also from a practical point of view, because it's really guiding the design of materials together with other quantities, but it's indeed practically very important and indeed somehow well established. On the other hand, of course, we all know that what happens somehow in between is also very important and a bit fuzzier. And so there have been a lot of discussion this week about some of these occurrences, delayed yielding, precursors, the interplay with shear bending, for example. I would try to briefly give you a couple of examples of discussing the, I would say, unexpected range of application of this simple number that we call yield stress. So I'm using for these experiments, I'm using carbopol microgels. They are composed of polyacrylic acid chains, which when neutralized in aqueous solutions, they swell, so that at some concentration, they will fill the space and provide a yield stress. So let me note that they are these widely used industrial materials. They are quite polydispersed, but they are sub-micrometer particle when swollen. So we extract their yield stress from flow curves. We basically can characterize the buildup of yield stress above a certain concentration. This is always mass concentration. Sorry for not writing. And so we see a clean onset above a certain threshold, a steep increase, and then a relatively slow increase, which we can sort of map with a picture like an arrested system above a certain concentration. And then in this steep part, we certainly still have some voids to fill, some gaps, while in this upper part, we are more and more sensing and probing the packing of them, that is their compressional modulus, which is anyhow provided by an osmotic pressure. And a relatively easy way to probe these extremes is whether to put a certain concentration of microgel, a sample, in contact with water through a semipermeable membrane, wait long enough, and what we are expecting, of course, is that it will suck some water. It may suck some water, and indeed, quite unexpected to me, I would say, whatever is the concentration you start with, if you wait long enough, you will end up very precisely to this concentration threshold. On the other hand, if you put in your bath PEG solution, you can exert an osmotic pressure so that you can tune the concentration of the sample depending on the osmotic pressure. And what I find quite nice here is that, okay, it's not the best graph probably because I would have to switch this to show you here the concentration, here the osmotic pressure, but this is the previous experiment. This is just with two different starting concentrations. But what I just want you to note is that there is a huge range of osmotic pressure which only lead us to a 1% concentration. Okay, Last practical observation about the sample, we can obtain a quite similar behavior if you do not neutralize the suspension. So if you concentrate microgels in water with no added soda, which I didn't tell you is what we're using to neutralize the solution, we nonetheless obtain a quite similar curve, of course, with a higher threshold and a somewhat lower osmotic, plateau value for the yield stress. Okay, and this is quite well known. I mean, you have a peak of the yield stress here. It's at 1% when you reach full neutralization, and then you have a further decrease back. It's non-monotonic. Okay, and this has been already observed for other carbopol systems. So I'm briefly telling you about two stories. One deals with the, let's say, validity of yield stress as a description for the untrapping of microparticle in carbopol suspensions, and the other is the motion of a small drop of carbopol on a surface. And I will almost certainly do not have time to deal with non-aqueous solvents. So a quite obvious consequence of the yield stress is that if you have a density-mismatched particle inside a yield stress fluid, if the particle stress is somehow smaller than a yield stress, it will be trapped. While on the other hand, if it's large enough as compared to the yield stress, it will flow, either sediment or cream. And this once again raises questions about what is indeed setting this threshold. What is how can we compare, how can we learn from bulk rheology to predict this behavior, which will have consequence on what is the region of the material that we are indeed probing and affecting. So just to give you practical, numbers, if we have glass beads 50 micron in diameter, you plug the weight divided by a cross section, this is less than 1 Pascal. So this is not very convenient to explore a range of behaviors, but we can artificially increase G, that is, we can plug the whole sample in a centrifuge so that we can have an effective gravity, so that we can scan a much wider range of behaviors. And this is just an example. I mean, if we suspend these glass beads in a capillary, we centrifuge it, we do see quite clearly that there is a discontinuity, a shallow discontinuity in the number of beads which remain suspended after a certain time. That is, at high enough gravity, at high enough gravitational stress, they get untrapped and they will disappear here in the bottom of the sample. So what is interesting, we can have a criterion for setting what I call a critical gravitational stress. We can compare this with yield stress, and indeed, this is nicely linear, proportional to the yield stress, but as you may notice, this is about 5 times larger, okay? And this is, it was already showed for much larger particles, and in the end, it's quite expected, I would say, but what I think it's interesting is that this by itself implies that it's not enough to reach the yield strain. If, as a particle, I want to go through the sample, I will have to fluidize a region which is largely exceeding the size of the particle. And this factor of 5 translates into something between 2 and 3 radii of the particle around the particle, microsphere itself. So how can we probe this? Certainly not watching inside the centrifuge, or not necessarily watching through the centrifuge. We scaled this down, and we did this with an optical force. It's a sort of optical tweezer. It's different. It's using, rather than gradient forces, it's using scattering forces. It has the pro that it goes up to stronger forces than optical tweezers. On the other hand, it's certainly less versatile. But together with people in Politecnico and in Pavia, we managed to have this in a rather convenient way so that we have a microchannel, and we shine light onto the sample, which is here in the channel. We have carbonyl here. We have a microsphere, which is 5 micrometers in radius. And we can literally switch on the light onto the particle. That is, we can exert a force, an optical force on it, which we calibrate. That is, we can conduct a creep experiment onto it. And so by properly defining strain and stress, we can compare this with macroscopic rheology. But we literally look at the sample, at the particle. So if you do it, you start with a dim light. What you see is that, a very tiny deformation that is recovered when you switch off the light. When you increase stress, you start seeing this kind of intermittent behavior, and when you switch off, you progressively lose part of the bounce of bouncing back of the backflow of the particle. When you exceed a certain stress value, you see that you transition to a sort of smooth but bumpy motion, which is continuous. But nonetheless, when you switch off the light, you bounce back a bit. Okay, and let's just look at it. We suspended smaller tracers here. It's a very rough sort of, to reconstruct the displacement field around it, very sparsely. But what is interesting, what I want you to know is that if you compare what happens at the maximum deformation, you have a certain amount of displaced beads, tracers, while when you switch off the light, you see that these are image differences. You see that part of this is recovered, but part of this is not. So this, once again, quite sparsely, but allows you to reconstruct a sort of what is the extent of the sample which has been plastically rearranged. So we may say fluidized in some sense. And so by running this experiment several times, what you see is that once you cross a certain value, which I forgot to say is nicely corresponding to the bulk yield stress modulus that we measure, what you see is that you quickly go up to a value which is somehow 2 to 2.5 times the radius of the particle. Somehow, once again, confirming that the correspondence between the micro scale behavior and the macroscale behavior is module the fluidization of the surrounding region, which we are not carefully reconstructing, but at least we can roughly estimate. Let me just make a super quick short note about this. What about these bumpy features? What is nice here, of course, this is more and more frequent as we increase the stress, and we can map this to the flow curves. But what is interesting to note is that despite the fact that we are increasing the frequency of such jumps, somehow the amount of this jump is rather constant, which is in the order of the particle or a couple of particle sizes. Okay, somehow consistent with the fact that this bead, which is 5 micrometers, in order to proceed, despite the fact that it's at least 10 times larger than the surrounding microgels, does have to displace these microgels and to cut through. Okay, so I will try to quickly go through this second set of experiments, completely different. Rather than this having a solid inclusion inside the yield stress fluid, we now take a drop of carbopol and we want to study its motion regimes. So with water droplets, that is quite easy. It has been super well established, of course. You can map this with, tuning the gravitational stress, and you have an effect of the surface tension on the shape of the droplet, which cancels out when you look at the speed at which the droplet goes down, so that in the end, the speed at which this goes down only depends on G, which we tune, and the viscosity of the water in this case. But of course, you immediately see that as you get into a more and more viscous fluid, if you get into a viscoelastic fluid, for example, such an easy experiment and nice description falls apart. And so in practice, what you would like to do, like the concrete experiment to test the yield stress, in practice for a small drop of yield stress fluid is not that easy. And indeed, if you try with PTFE or hydrophobic surfaces, you often get stuck, okay? Or, like in this Ewald example, I mean, you drastically have to rearrange in order to get out of this trap, okay? So in practice, how do we describe and face this? A nice trick is to use lubricant-impregnated surfaces. That is, we trap a tiny layer of oil onto the surface so that we obtain a very low roll-off angle for the for sliding down or whatever happens. And indeed, it was some years ago demonstrated that this was even able to produce motion in this teddy bear or so of an yield stress fluid. So the setup is quite simple. It's based in Padova. We tilt with controlled angle the sample, and we look at what happens. One important thing to take care about is that while a simple liquid will basically stay fixed, its contact angle, its size will remain fixed over time. When you drop not a teddy bear, but a real drop of yield stress fluid, it will tend to spread over time, but it will reach a plateau value. If you want to know more, ask Masi and these nice experiments on spreading and numerical simulations on the spreading of a drop. But it makes sense that this will locally fluidize and tend to spread, okay? Even though the boundary conditions were different. So what we do after allowing enough time on horizontal plane to set up, we incline the plate, and what we see, it's basically two different possible regimes. So we take this, we see that this droplet will tend to roll down. We do so by suspending small tracers into the sample and tracking them. Just very quickly, you see rolling for a high enough angle, but if you do the same for the same sample, but at a smaller angle, you will see that this will slide down. On the other hand, if you take the same angle, you weaken the sample, that's a smaller concentration, you'll see the rolling recovered. So you can trace a sort of phase diagram concentration in the inclination angle, and you see some sort of transition, crossover. Motion is observed virtually at every measurable angle in this system. And let's think about what is happening when we see sliding, which is in this part, okay? So what is happening indeed is that basically a solid droplet will surf on the oil layer. And we can compare this and we can try to see if it makes sense. So we can measure the speed of the droplet, and we can assume U here is the velocity. We can assume that the viscous stress, H is the layer thickness, B is the size, the height of the droplet. The viscous, and here is the viscosity of the oil. The viscous stress will somehow be the same as the gravitational stress, from which you know almost everything. You can estimate this, which definitely makes sense with the preparation protocol, which is a sub-micrometer layer of oil. On the other hand, Okay, of course, we can map and translate concentration into a yield stress, inclination angle into a gravitational stress. And if we look at our phase diagram as a function of the ratio between yield stress and gravitational stress, what you see is that you have a sort of fuzzy but crossover between a rolling and a sliding drop, which is somehow around the values of gravitational stress which are exceeding the yield stress of the material. Okay, so we have no real local proof yet of this, and it would be interesting to look locally at what's going on inside the sample, because I guess that there will be some sort of closer region to the substrate which will be affected way more than the upper part. Okay, this is not that important. Let me just note that indeed this crossover was already proposed by a previous group with different sample, much bigger droplets, and they were also dealing with, in an arguable way, with an adhesion, a sticking portion of their phase diagram. Okay, do I have one more minute? Yeah, okay, I would have had even more, but I would just spend 1 minute and do not prevent you from your coffee. I will just only tell you why we're playing with non-aqueous solvents, microgels in non-aqueous solvents. We were somewhat inspired by a paper by Migliozzi et al., a London group, playing with glycerol and small molecular weight PEG. And this is, of course, also interesting and relevant for industrial purposes. And so we're quite skeptical at first. This is what they show. They're clearly not very well dispersed because you have these big chunks. These are non-neutralized solvents, and somehow we try to play around with different solvents. You can somehow wonder what is well connected to water in terms of polarity, whose proxy is the electric constant. We can have better estimates based on much more complex methods, but you end up with some sort of correlation, the gray values, with expectation for dispersibility of carbopol in a bunch of solvents. We tested some of them. Some alcohols are indeed not good in dispersing carbopol, while some are borderline. You would predict by this method water, glycerol, and propylene glycol not being able to disperse carbopol. And indeed, in some sense, water it's not, unless you tune its pH. And somehow the same, surprisingly, is also happening, for example, for propylene glycol and as well for glycerol. So somehow, surprisingly, we found out that we can suspend carbopol in non-neutralized propylene glycol, this blue curve. But if we add soda in it, we increase the dispersibility, which means we decrease the threshold, we increase the overall plateau value, and we're still trying to figure this out. But what is nice is that we have a sort of, this is the yield stress once again for various concentrations in PG as a function of pH, and we always have a sort of peak, and we have a clear rheological signature somehow of the full swelling of our microgels in different solvents. With this, I think I'm done. I think that the take-home message is yield stress, after all, is a quite reliable number, which is also sort of weird statement here. And microgels, despite being carbopol in particular, despite being a super well characterized and established microgel material, still provides some new interesting things to find out. And with this, I'm done.